Good morning, everyone. Thank you so much for registering and welcome to the day one of our live online training on Metabolomics data analysis in the cloud. My name is Namrata Kale, and I'm working as a project manager for PhenoMeNal Metabolomics team at EMBL-EBI. Our first session today is on getting started with PhenoMeNal, presented by Dr. Pablo Moreno, who also works at the EMBL-EBI.
Hello, can you hear me? Yes. Hello, my name is Pablo Moreno, as Namrata introduced me. I have been the tech lead at the EMBL-EBI for the PhenoMeNal project for the past 2.5 years now. And I'll be talking to you today about, I'll give you a general overview of PhenoMeNal, and I'll give you a short demo of how you can use our ability to deploy a metabolomics data analysis infrastructure to a cloud provider. I hope you very much enjoy the demo that I will give. I will give some links as well to where you can find the instructions to follow on the demo on your own time, so you can try to reproduce this, and also to be able to get an account in our public instance. So now we will go on with the slides for the PhenoMeNal overview part. So to start with, I will talk to you a bit about what is. So we will go through this presentation first to understand what is a bit cloud computing, as it's an integral part of PhenoMeNal. PhenoMeNal is a project that is envisioned to allow people to work doing metabolomics data analysis on the cloud. And then after that part, I will give an overview of the main components of PhenoMeNal, and I will explain how they interact to be able to provide the functionality that I mentioned before. And once we've done that, I'll go through an overview of the different tools and workflows that we have to finalize with a demo where I will show the deployment to a cloud provider and the access to our public instance. I hope that you enjoy this presentation. So to start with cloud computing, I would like us to reflect a bit on how do we run the processes that you see on the screen currently. So if you think about sort of a power provisioning to your house or to your workplace, you don't normally have something like a generator wired to your house, to the external part of your house. If you think about the provisioning of potable water services, you probably don't have a huge tank of water on top of your building, but most probably these services are today, and for many years now, being delivered through networks of electrical wiring, networks of water pipes that take water or electricity from a central distribution point to the point of usage. If you think of how you do computing today, most probably you would sit at the left-hand side of the picture. So you get most of your computational power today physically with you at your workplace or at your home, very differently to how you get electricity or water services, which is provided through a network. So the whole idea of cloud computing really is from switching from this model of local sort of a computational power provisioning to a model in which you get these things in a different way, in an unlocalized way. So in the 1960s, Professor John McCarthy at MIT came up with the concept of utility computing. He essentially said that computing may someday be organized as a public utility, just as the telephone system is a public utility. The computer industry could become the basis of a new and important industry. However, at that time, we didn't have the technological advancement, we didn't have the network capabilities, we didn't have the hardware capabilities to be able to realize this dream, this conception. However, that has been happening now for the past maybe 10 years or so, where the hardware and the networking capabilities have really allowed us to really fulfill this concept of utility computing, of cloud computing. So what are the main characteristics of cloud computing compared to normal computing? First is that we all run what we want to run on shared resources. So we all share the computer hardware that is going to execute the different things that we want to do. We don't necessarily own it. We just have access to it, or have sort of access to a certain amount of time or a certain amount of resources. Very much as the other services that I presented, water services, electricity service, cloud computing you use through a network, through a computer network in this case. So you might have a terminal, a computer, a screen even on your desktop, but most of the computation you do on a remote location through a network. It also needs to be, every application or everything that you need to run here needs to be rapid and simple to set up. Okay, that means that if you want to have an email server running to check your emails, it needs to be able to quickly be installed on these computers, start to run quickly, and then once you stop using it, it's taken down. Because it's rapid and simple to set up, that also makes it scalable. So if you have an application that you need to run that needs to process more and more data, right? You can have more and more copies of your software being installed and run on more and more machines in this shared environment. And this makes it scalable because it means that you can process higher amounts of data, or you can process peaks of data in a particular time frame without having to own a huge amount of computers, but only having access to those computers for a very short time. It's normally a pay-as-you-go service. So you use 10 hours of computations and you pay just for that, which can amount to very little money in the end compared to having to actually buy a computer, having to actually buy a building where you house all your computers, people to maintain it, air conditioning, etc. So it becomes a lot cheaper per the hour if you want. So the fact that we can automate the setup and that we can do a rapid and simple setup, it's key for cloud computing. And how do we do this? So if you think of how you do an installation of software today in a computer setup, you essentially have maybe a set of machines, a set of computers that you have maybe in your lab or at home. You might have access maybe to a database server. You put an operating system on top of the computers. Then you put some software that you want to run, like R maybe, or particular R packages, Python, etc. Each one of these things is sometimes tricky to install for different reasons, but it tends to be a relatively manual process. So you do the manual installation of the operating system, you do the manual installation of the software, you do the manual configuration of the hardware. You might have even bought the boxes and put the memory inside, etc. In contrast, what we do in cloud computing is that we write all the setup that we want to have in a machine readable format, and then we can distribute this as a file. Okay. And once we have written all the specification of what we want, what are the machines that we want, with how much RAM, with how much CPU, what are the programs that we want, with which operating systems, which softwares are we going to run on top of that. When we have written all of this setup in this machine readable files, it means that we can very easily replicate that setup in different places, in different cloud providers, as you call them. So what used to be a very manual setup, where you would do everything on your own and where you would sort of be sitting in front of the screen installing each of the components, it becomes an automated setup once you have this definition, which you can deploy at various different places or multiple times at the same cloud provider, making your application elastic and scalable. There are, of course, a number of challenges in doing this, but that's the main idea behind the automatization of the setup. And this is putting all of this setup here is what you call infrastructure as code, because you are codifying all your infrastructure, and it's a key aspect of being able to automate the setup. So compared to non-cloud computing then, one of the disadvantages of legacy computing or non-cloud computing is that it has higher costs, it's less flexible, and you have it has higher costs, of course, because you need a building, you need people to maintain it, you need to actually buy the computers. So it has a lot of fixed costs if you want. It's less flexible and you have more lock-ins, basically because you bought a set of machines. You bought maybe 100 machines to a particular provider. You are maybe bound to use certain system software for sort of a warranty reasons, maybe. Once you have set up the system, normally your users have less flexibility to install things in there. They won't have administrative rights, etc. But on the other hand, of course, legacy systems do have their advantages. And one of them is that you might have already databases at your university, or you might have data sets that are in a particular hard drive, and all of those are already working with your legacy systems, with your computer cluster, with your high-performance computer system. There's also less of an expertise gap, and I will go very quickly into that soon. But essentially, with the previous model, you get machines, and you get a setup, and you get people that works in your institution to do the setup. Whereas in cloud computing, you essentially just get resources. So let me go into the expertise gap by explaining first what you get when you start with cloud computing. So on the cloud, what you essentially get are resources. So you don't get machines anymore. You don't get hardware anymore, but you get just amount of CPUs that you can use, an amount of RAM that you can use, an amount of storage that you can use, but you don't get actual physical machines with anything installed. So how does this affect the expertise gap that you need to be able to exploit IT resources for your research? So in the current model, the non-cloud computing model, what you have is that you got some funding probably, which allowed you or your institution to buy some hardware. So you have a set of computers in your university, you have maybe a cluster, right? On top of this set of computers, some people from your IT department or a bioinformatician might have set up a Unix system, might have set up a database engine that you're using, might have set up a cluster for sending jobs, might have set up different web applications that you can use to do your research. So the gap is essentially that one, from you and your research to all of these elements being set up for you by someone else. Now, sometimes, of course, there's a lack of manpower in these sections, and you might still suffer a bit from that. In contrast, initially, the expertise gap in cloud computing is a lot larger, because differently to the previous model in which you had some hardware, in the cloud model, you start from your funding, but you essentially have a cloud tenancy with resources. So you have an amount of RAM that you can use, you have an amount of CPUs that you can use or buy, but you don't get any of these already set up for you. So it means that you need to go from raw CPU, from raw RAM, from raw storage to actually do your research, which means that there's a larger knowledge gap there, because you will need to know how to set up a plethora of things like virtual machines, containers, etc., that most people are not interested in doing when they are doing research, of course, because they want to focus on their bread and butter. And this is where scientific cloud infrastructures like PhenoMeNal really help you. So they allow you to get all the advantages of the cloud computing model in terms of scalability, in terms of using more data, and so on, but without having to do all of this setup that you need to be able to do actual research, which means that PhenoMeNal as a scientific cloud infrastructure helps in narrowing this gap here, so that you can do your research more, or you can use IT resources more easily for your research. So with that, I will step into our consortium as such. So the PhenoMeNal Consortium is composed of 14 partners. We got a granted Horizon 2020 project for a 3-year period led by EMBL-EBI with the partners that are shown in the map. And this is all people that have plenty of experience in dealing with large data problems in the fields of metabolomics. So the current scenario in data analysis in metabolomics is that people use their analysis locally on their computers today, right? So they use certain tools, certain workflow environments, maybe they access certain private and public data on computers on their institution, that be on their lab, on clusters in the university, etc. While this is very good, it means that if you have a data set that is maybe 10 times larger now or 100 times larger, it literally takes you 10 times or 100 times more to analyze it. And because setting up all of these tools is difficult, all of these bioinformatics and metabolomics tools is difficult, taking this to another set of machines that is larger, where you could run your analysis faster, is very difficult. You would need a lot of manpower to be able to do the same setup, to be able to take that compute ability to some other place. So our proposal in PhenoMeNal is to take you to be able to run your analysis with the same tools, the same workflow analysis environments, being able to access the same data, but on an automated setup that you can deploy on the cloud so that you can scale very easily. So you can use a few computers if you have a small analysis to run, but you can use many, many computers if needed. I'm sorry, I need to adjust something here on my setup because for some reason this is using the timings. If you bear with me a second. Okay, let me get rid of that. I'm sorry about the impasse. Okay. So as I was saying, this allows you to scale in your analysis. So if you suddenly have now a data set that it's 10 or 100 or 1,000 times bigger than your previous data sets, you simply can use more machines. Or if you are in a hurry and you need to have your analysis done faster, you can always sort of scale up, use more computing power on the cloud with the same analysis tools and get your results. And I will show in the end some examples of how this was sped up for some analysis. So why do we need, or would you need PhenoMeNal? Well, if you don't have any programming expertise to be able to deal with maybe our tools, then we have a number of metabolomics data analysis tools in R and Python that are already packaged and installed for you, so you don't need to worry about installing them. You don't need to worry about dealing with their dependencies, which if you have installed scientific software, you will know that it's a complication many times. You can do larger data volume analysis and transfers compared to the previous case. This in turn allows you to scale in your analysis, as I was mentioning before. You have less maintenance on software because of the way that we package software for you. So you don't need to worry about different versions of things because we take care of all of that. And most importantly, it allows you to move the compute to the data. So if you have a very large project in which you are ingesting data somewhere, and it's very difficult to move the data around networks, you can always deploy in a cloud provider that is close to where the data is ingested. So what are the components that allow us to bring this functionality to you, the ability to run your metabolomics data analysis in the cloud? So the first component, and where you will first have a contact with our setup, is the PhenoMeNal Cloud Research Environment portal, which is available at the URL that you see there. The PhenoMeNal Cloud Research Environment portal is the place where the user will go to be able to deploy or to create his own or her own cluster of metabolomics with metabolomics data analysis tools automated by PhenoMeNal on a cloud provider of choice. Then to be able to do this, to be able to put all of this automated setup on cloud providers like Amazon or Google or private cloud providers like OpenStack, we had to build the infrastructure and put it as code. So what I mentioned before, the ability to automate this setup everywhere. And this allows us to create for you a small cluster or a larger cluster of computers in one of these cloud providers. Of course, to be able to run the tools on top of this infrastructure that we create for you, we had to package tools in a certain way so that they can be seamlessly run on top of this infrastructure. And for that, what we did is what we containerized a number of metabolomics data analysis tools that are relevant and that people tend to use these days. And I will go later on the detail of how many tools we have and how they are organized in the metabolomics analysis space. But also, in order for you to be able to use these tools on this infrastructure, you need to have the data that you use packaged in a certain manner. So we have been working with data producers as well to make sure that the different standards in data formats and packaging can be read by our tools on top of this infrastructure as code that we deploy on the cloud providers. So how do these elements interplay and how do you as a user interplay with this? So imagine that we have a user that has an account in a cloud provider. So in this case, Amazon Web Services. So this user would initially visit our cloud research portal in the URL that I mentioned before and that you will have access later as well. And the user will request the creation of his own cluster of computers on the cloud, his own cloud research environment, as we call it. So the cloud research environment portal will then take our infrastructure as code definition, go to Amazon, and create for the user its very own cloud research environment. So this set of machines that are being set up in Amazon for the user now only belong to the user. The user doesn't have to compete with any other person in the world to use these resources. So you are no longer in the queue for running jobs. And once this setup is ready, the user then can go directly to the PhenoMeNal Cloud Research environment created for him or her at the cloud provider and start doing some work. And for that to happen, and because we don't want the user to have to deal with command line interfaces or having to do any programming on the tools or any scripting, is that we provide workflow environments with user interfaces that the user can use to actually execute the different tools and workflows that you require to do metabolomics data analysis. And as the user starts to use these workflows and invoke different tools, the different tools get pulled into our cloud research environment. This means that the setup of this is relatively lightweight, and it takes in the region of 15 minutes or roughly that. But it's a lot faster than previous setups that were available before the era of using containers in the cloud. So to get an idea of the amount of tools that we currently have around 180 modules that are available for you to use in our workflow environment. 5 of these tools are meant for data transfer, so you can get particular data formats from particular providers of metabolomics data. We have tools for dealing with metadata, so you might be aware of the ISA standard. We have tools for converting between metadata standards, such as Workflow for Metabolomics and ISA. We have tools for metadata validation. We have around 12 tools for NMR data analysis. We have more than 100 tools for mass spectrometry data analysis in between XCMS, OpenMS, and the DIMSPY package. We have an additional set of tools to further process the initial preprocessing in mass spectrometry. We have tools to deal with carbon-13 based fluxomics in mass spec as well. And we have tools for statistical analysis and post-processing of your NMR or MS pipelines. We also have in the region of 8 pre-assembled example workflows in mass spectrometry and NMR, mostly in mass spectrometry, which is currently the stronger part of the setup. And we have Galaxy tools, which allow you to have a walkthrough how one of these workflows would work and understand how you would provide data to them. And all of this is based in around 50 software containers that for more advanced users, they are freely available to be used directly as well. So this is a bit how the workflow environment that we have sort of looks to you when you are dealing with data and when you want to do an analysis. This is the case in particular for the carbon-13 fluxomics data analysis. So what you see in the workflow environment is these boxes, where each of these boxes represent a step in your workflow, a particular tool that does something that you're interested in. And what happens here is that once you set up the input data for the workflow will go on different steps using different set of tools to generate the different output files that you want to see and the visualization for them. We have more examples, for example, for mass spectrometry, the MetFrag pipeline, which was created by our collaborators at the Stefan Neumann's group in IPV Halle. We have a more exquisite workflow for analyzing jointly MS1 and MS2 data, where you can actually cherry pick modules between XCMS and OpenMS, again developed by our collaborators at IPV and our collaborators at Uppsala. We have a working NMR workflow that allows you to take some data from metabolites from certain NMR experiments and produce some results. And this was developed by a number of collaborators within our consortium. We have the direct infusion mass spectrometry workflows that allows you to take care of this type of MS flavoring, developed by our collaborators at the University of Birmingham. And as I mentioned, we have statistical analysis workflows to be able to take the results that you have from an MS or NMR setup and be able to do the statistical post-processing, mostly developed by our partners at CAE at Paris in France. So I mentioned that you can easily scale with PhenoMeNal, and this is an exercise that our partners did in Imperial College London, where they installed the PhenoMeNal setup in different set of machines, in different set of clusters, if you want. So they started with a small desktop computer that had 8 cores. They went on with a larger setup that had 50 CPUs. Then they moved into a cloud provider, Microsoft Azure in this case, with a setup of 300 virtual CPUs. And finally, they used the Embassy Cloud here at the EBI, using 1,000 CPUs to resolve the same scale of the problem, with different amount of. And so what you can see is that as you use different amounts of the CPUs, the speed up ratio, so how much faster you go because of using, how much faster you go because you use more CPUs, it scales relatively linearly as you use more CPUs. Okay, so the more CPUs you have available to solve the problem, the faster you can go, nearly linearly in most cases. So if you can access for the same problem that you have 10 times the capacity in CPU that you're currently using, it means that you could have a 10-fold speed up for your problem. So it becomes 10 times faster to solve it. Is there any value for money real in metabolomics? Well, we continue with the example that our partners at Imperial College made. What they made initially is that they run 2,000 spectra on the Azure Cloud Platform with 300 virtual CPUs. And that has a cost on Microsoft Azure of around $17 per hour. Now, the system deployment took 10 minutes, and then the runtime with 300 CPUs took 22 minutes, which amounts to $6 just of the runtime time. So it took them less than 30 minutes to do the whole analysis, and that was less than $10 of expenses. This is comparable if you think of the case where you're running this on the desktop system with 8 cores, and there, because they had only 8 cores, it took them 15 hours to run compared to less than 10 minutes. Being able to buy that machine, it probably had a capital cost of $1,500, but there are also other costs like maintenance, support, space. You could, of course, argue that you would have this machine for a very long time as well, but for the purpose of sorting out this exercise, there's an apparent price advantage on this if you are not bound to do this initial capital cost investment. For a medium job of 200 spectra processed with the same tool in the same setups at both sides, on the Azure platform with 200 CPUs, not 300 now, it took 3.3 minutes and it cost less than $1. Whereas in the desktop machine, it would have taken 1.5 hours. So you can see the differences in cost and time that you can achieve with this. So I'm going to step now into the Cloud Research Environment portal demo. The Cloud Research Environment portal allows you to do the cloud deployment of things to the cloud. It gives you access to our public instance, which allows you to try what you would get in a deployment to a cloud provider without having to pay. So that's getting an account on our cloud deployment. It has an app library where you can see all the elements that we have available, and you have access to documentation. The CRE portal, when you go there and once you are registered, will allow you to deploy to to our Amazon cloud, to our PhenoMeNal cloud, which it's essentially getting an account on our setup, but also deploying to the Amazon Web Services cloud provider, the Google Cloud Platform, or OpenStack, which is a private cloud provider that many universities have installation for today, and where you might not need to pay anything for. To get an idea, to run our setup for 24 hours on Amazon, it costs roughly around $20. Now, this is something between you and Amazon. We only provide the way for you to get everything automatically there. We don't get any dollars for ourselves in the middle. This is completely between you and Amazon, or the cloud provider of choice. So now I will start with the portal walkthrough and deployment practical. I will show what the portal is. I will show you how to get an account on the PhenoMeNal public instance. I will show a deployment on Amazon Web Services. And all of the steps that I will follow are part of the hands-on number 1 on the address that you have here. Okay, so you should be able to have access to the URL on the notes, which someone will paste soon if it's not there. But you all have access to the slides, if I'm not mistaken, so you should be able to see this URL individually as well. You can, of course, replicate this exercise on your own time. You don't need to do it while I do it. So I suggest that you just relax and take a look at what I'm doing. And if you have an interest, of course, you could try to follow up the steps. Try to follow up the steps later on by following this URL. Okay, so I will proceed now with this. So this is where the notes are for this module. So you would have to go to this hands-on one once you want to replicate this later on, and follow the instructions there. And you will have here all the steps that I will go through now. So this is the PhenoMeNal portal, which is accessible in this URL, which is available in the tutorial that I pointed out before. So the first thing that we will do is that we will show how to try our public free instance. So I will click here on this button that says try our free public instance, which will allow you to access directly our Galaxy setup, our workflow environment setup on the cloud. So this is how our public instance looks like. And you will be able to try different tools that we have for this. So I mentioned we have plenty of MS analysis tools, as you can see here, different XCMS tools, different OpenMS tools. The ones that have a P are relevant for proteomics as well. You have NMR data analysis tools, and you can explore on your own, of course, the metadata section, getting data, etc. So now I will go back to our portal again, and I will now show you how to create your own cloud research environment. So for this, I will go and press on the button here, create your cloud research environment. It will ask me to log in through the Elixir sign-on, which essentially allows you to reuse accounts that you might have on other authentication providers like Google, like LinkedIn, or like Orchid. So you don't need to recreate accounts with us, but you just reuse your existing setup with one of these providers. I will use, in this case, my Google account. And Elixir will ask me whether I want to release my personal data to PhenoMeNal and EMBL-EBI. I will say yes here. And because I've used the system before, I didn't get to the terms and conditions, but you might get into a screen of terms and conditions to ask you to accept that. And this is shown in the tutorial part that you have access on the other URL. So what I'll do here is that I'll first set up a run on Amazon, because it takes a little while to spin up. And then I'll go and show you how to get an account on our public instance. So before I show you how to get to our public instance, but if you want to really store data and run workflows, you will need to get an account on the public instance. So first with Amazon now, I will choose Amazon Web Services here. So Amazon is asking me to enter my Amazon credentials. So this means that you need to have an account with Amazon where you have credit to be able to use their Amazon Web Services. Okay, so I have already an account. I will first choose the region of the world where I want this deployed. So I will choose Frankfurt. And then this is asking me for an access key and a secret access key, which are part of the credentials that you will get if you have an Amazon account. So I will briefly copy my credentials. Okay, I will press next. So now he's asking, the interface is asking me to set up a password to secure the environment that it will create for me. So once PhenoMeNal creates for you your cloud research environment, your cluster of computers for doing data analysis, you are in control of it and you are the administrator there. So you need to have a password to be able to secure it. Okay, so this is a password that you just invent and that we don't store for the, well, we do store for a short time so that you can log in. So it has confirmed my password, and now it's asking me to confirm the details, and hence now I can press deploy and everything will start rolling. So what you see here is that the new setup is starting, okay? And you will see this bar progress until the cloud provider is created. So this process will take roughly in the region of 15 minutes or so. If you are sort of more technically inclined, you could also click on the logs here and you will see what is going on behind the scenes. I will skip that part for now, but you could be able to do this if you're interested while you replicate the tutorial. So in the meantime, and while I leave this running, I will go back to the setup where I can create my account on the PhenoMeNal Cloud Research environment. So I'm already signed in here. So what I will do now is that I will press again, create your cloud research environment. But this time, instead of selecting Amazon, I will select the PhenoMeNal Cloud. So what happens here is that the PhenoMeNal Cloud will ask me for an email to be able to log in. So this is presenting what the PhenoMeNal Cloud is. This is currently being run at EMBL-EBI in the UK. So if I press login, it will take me to the setup. Okay, so there's a tiny glitch here. So because I've used the system before, I don't get the input screen that you would get initially to register, but this essentially looks like this. So if you go to the tutorial that we have here, once you ask to register to the PhenoMeNal Cloud, what you will see is a screen like this, where you will be asked to create a password for the email that you are registered with when you sign on with Elixir. So it will reuse the same email and it will indicate you which email is that. And once you've done that part where you put your password and you confirm it, it will create the account for you on our public instance. And then when you press the login button, as I did here, it will take you to the place where you can put your credentials to log in. So I can write here my setup. Hopefully I remember the password that I used for this one. And now this has logged me into the PhenoMeNal public Galaxy instance available at our cloud. So because the setup is automated and it's always the same in the different clouds, it means that the result that you get, regardless of on which cloud you're running, is exactly the same. So the user experience that you will get, it will be very, very similar. The only variation could be that certain cloud providers might have sort of better hardware or not, but the user experience in terms of the tools that you can use and the interface, it's always exactly the same. So now I will try to go back to the cloud setup that it's running. So this is still running, but what will happen once this is done is that you will see a screen like this, where you will be given the ability to choose the different services that we provide to be able to log in on your own Amazon deployed cloud research environment. So you will be able to click on Galaxy and you will get into Galaxy with the email and password that you set up during the process. So with that, I will leave a small time for questions. So let me get very briefly to the slides. As a conclusion then, PhenoMeNal is a scalable cloud infrastructure for metabolomics data analysis. It's a point-and-click deployment setup that allows you to very easily have a small cluster of computers to do data analysis. It provides you with workflow environments where you can use different tools to do the metabolomics data analysis that you're after. If for whatever reason it's not working for you, we would really like to know how we are not being able to adapt to your needs. So please talk to us. We would really like to know that feedback. And with that, I will thank you for listening to this presentation. And we can start with some questions after a short 5-second break, right? Okay, so we have some questions already, right? So Gamal Akabani is asking whether Galaxy is if Galaxy is different than PhenoMeNal. So Galaxy is a component that we use in PhenoMeNal. Sorry, just a second. So Galaxy is just a component that we use in PhenoMeNal. You can have other Galaxy installations provided by other people. Galaxy is an open source project, so you could even have your own flavor of Galaxy, right? So it's just a component that we use in PhenoMeNal and that we sort of customize so that it fits into the needs of metabolomics data analysis. We also did a number of developments on top of Galaxy so that Galaxy could run on a cloud environment. So that is a contribution of this project to the Galaxy community. There's another question asking, can we create a cloud research environment on PhenoMeNal without using Amazon? So yes, you can, provided that your institution has a private cloud provider. So if your institution has something like OpenStack, for instance, installed, your university or your research institute has OpenStack, then it means that you can use our deployment setup to create the same PhenoMeNal cloud research environment on your local OpenStack setup.
Thank you, Pablo, for presenting this. If you have any further questions, please use the Slack channel